also, in this framework, I mean, we input the kind of metric and then solve the digiton and digiton potential. So, but anyway, in any case, this digiton field and the metric structure should be solved self-consistently. So basically, well, but if you input the metric, somehow you don't know, you don't know the dynamics from the metric, right? So, but anyway, they connected with each other. So of course, I mean, you can calculate the running of the Yamir's gauge theory. I mean, because this digiton field is related to this coupling constant. So you can calculate this beta function in this framework. And then, for example, with our input, we can say that, I mean, we can calculate this beta function and compare with perturbative QCD result. And we see that, okay, it's not that bad. So, yeah, but I may skip this. And now I come to this work because previously I just show you that with some naive try that, okay, you can get something correct, but maybe you don't understand what's going on there. So actually, I think this work actually, I think we put a lot of efforts, especially my student Danny, he put a lot of efforts. And I think we made some progress that we built such kind of a systematic framework that, so we call now this framework as a dynamical holographic QCD model. And in this model, actually, we can somehow resemble, I mean, this model can resemble the RG flow. So this is finished in this March. So this is the, okay, so basically of course, I mean, if we believe that holographic duality is a kind of general principle, if we believe. And then, so basically, in some sense that, so if we believe that for any d-dimension quantum field theory, there is a kind of d plus one dimension gravity dual. Of course, now, I mean, it's a kind of assumption, or it's a kind of belief that, okay, this should be like that. And actually, I like this review article very much because it's quite give us much insights. And so basically, the holography is kind of emergent critical phenomenon in many body theory, right? So when the system is strongly coupled, some new weakly coupled degrees of freedom can dynamically emerge, and this actually emergent fields is a kind of living in a dynamic space-time with the actual spatial dimension. So this actual dimension plays the role of energy scale in this quantum field theory. So actually, this resembles such kind of resembles a renormalization group flow, and this is. So, for example, when you consider the cross-granular spins on the lattice, so this is your you put this spin system on this lattice. So this is your UV. This is kind of you put this Lagrangian at UV, and this is the operator, and this is the coupling. This is the coupling. This is the coupling of the source, and this is the operator. You put this system on your lattice, and you do the simulation. But with the lattice spacing changing, So with the lattice space changing, so basically this coupling also changes, right? And this coupling constant changing, so basically give you this beta function. So this is a kind of running, so RG flow that, so maybe what you are interested in is this, what happens at the IR region. So even though you only know the Lagrangian at UV region. So what you are interested in is actually the system at IR. So but this RG flow gives you this. And so now, okay, so you can, so this does not work too much. So in some sense, this quantum field theory on the lattice equivalent to the RG problem from gravity. So you can, so for example, this RG scale, you can promote this RG scale U to an extra special dimension. This is like this. And the coupling constant, you can promote this coupling constant to a dynamical field, right? So basically, it's kind of, this is equivalent. So you can solve the quantum field theory on a lattice, or you can solve this RG problem from this gravity. I think this is quite interesting. And so of course you still need some kind of connection between this operator and this bulk field. And this is actually the only thing we need from the ADS-CTP dictionary. This is from the ADS-CTP dictionary. So if you know the dimension and then you know the fifth dimension mass for the bulk field. And then of course you can solve everything from this system. But of course, I mean, if you can solve, of course, you need the strong coupling limit for the quantum field theory. Okay, so now with by using such kind of scenario, so we can cook up a kind of quantum dynamic holographic QCD model for the pure gluon system. So this is actually this worked quite well. So this pure gluon system, so it's so basically this is just Lagrangian for the pure gluon system. And at the IR, of course, we have gluon condensation. And we can construct such kind of graviton-dilaton system that we introduce a dilaton field. And this dilaton field here, of course, we need such kind of dimension 2 dilaton field. But now I don't want to get into some trouble. But anyway, you will see that we really need such kind of quadratic term for this dilaton field. And this dual, of course, this is a kind of, because this is a gauge invariant dimension 4 condensation. But because this is dimension 2, this is dimension 2 dilaton field. So basically we can do this, we can introduce such kind of duality. But actually this again gets some trouble from the referee. But anyway, yeah, because, but anyway, but in some sense, I mean, this is quite essential to get the right answer. But we cannot avoid that, this dimension 2 dilaton field. So, but anyway, I don't want to get into trouble here because anyway, it doesn't matter, but we need it. So the essential point is that we need such kind of quadratic dilaton field. Okay, then with this, basically we have this digital field, and this is actually the same as the software model or the KKSS model. So basically this is the same quadratic term. And with this, then we can, with this digital field, we can solve this digital potential and as well as this matrix structure. I mean, we can solve this self-consistently, and then you will see, okay.
So what was in the potential, in the V?
The potential can be solved analytically with this digital field. Yeah, so I mean, with this is the input. This is the input, and with this input, you can solve this V5, and also this G, this matrix. Okay. Yeah, okay, this is better. Okay, so basically, either you input this, you solve this and this. Either you input this, solve this and this. But I mean, if you input this and this, it's kind of, I mean, we don't know what happened. So I would like to input the field because from the duality, we can read some kind of information from the QCD side. Yeah. Okay. So this is like I mean, for this pure gluon system, I mean, our graviton digital system looks like this. So basically, at UV, it's asymptotic ADS5. But at IR, basically, we introduced such kind of gluon condensate. And of course, this gluon condensate is resembled by this digital field square. Yeah. So with this, then we can solve our global spectra. And of course, we compare our results with the latest data. So there are several groups. They calculate the global spectra. This is only for scanner global. And you say that. Okay, so of course so here this is our digital field, and this is the solved matrix, and then we introduce the global field. So we solve this equation of motion, and of course this is scalar global. This is due to this G squared. And from the ADS-CTP dictionary, so we can have this 5-dimensional mass square is equal to 0. So with this, then we can solve the spectrum. And so if we only have ADS5 matrix, so like KKSS model, so they introduce the quadratic digital field, but they keep this ADS5 matrix. Then they can basically this is kind of analytic result. So this is basically an exact result in this manner. But you see that with this spectrum, you see that either you can get the slope correct, either you can get the ground state correct. But you can never get both slope and ground state correct because I mean you can fix one, right? You can fix one, but you cannot. Anyway, you cannot get both correct. But something very surprising happens that if we solve this our system, so basically we introduce the digital field. And we solve this software model, basically the back reaction from the digital field to the matrix. Then we found that this global spectra actually agree so well with this net state. So this is a kind of surprise. So it's kind of okay. This so this basically both the ground state and the slope are correct. And comparing with this KKSS model. So it's kind of this back reaction gives you the correct background of this system. So I think this is a surprise, but though I don't know some deep reason for that. And well, I may skip this kind of analysis. Yeah. Okay, now come to the confinement. As I mentioned that if you have a software model, this KKSS model, you even though you have a digital field, but because of your metric is ADS5, so you can never get linear confinement because in this model you have ADS5 metric. ADS5 metric only gives you the quantum potential. So, but in this framework, if we solve this solve out this metric self-consistently, then we can get this linear confinement for the heavy Cocker potential. So basically, sorry. So basically, in this model, the only thing we did is that we just solve this self-consistently. Then it seems everything is correct. Okay. Of course, now I'm talking about the glue, only the pure glue system. But now we want to add flavors on this pure glue system. So this is actually not very trivial. So actually what we did is that, okay, so maybe I briefly review a little that what efforts has been made by some other groups to improve this KKSS model. Because this KKSS model, they solved this rigid spectra only for row mesons. But actually, there are some problems in this model. Because, for example, the main problem is that they cannot get everything correct. So, for example, as I showed that if you choose this how do you say, chiral condensate, this chiral condensate is around this vacuum, from the very similar to this value, then basically you cannot get this the splitting between the chiral partners. So basically, all the chiral partners actually are degenerate in the KKSS model. And there are some groups that, for example, this group by Kapusta, and they made some efforts to improve this KKS model. And they introduced a kind of quadratic interaction in the scanner channel. So basically they introduced this X force. And they found, it's kind of improved, but somehow there is a kind of elective mass square for the scanner meson. So this indicates some kind of instability in such kind of framework. And also this framework, some improvement made by ITP group, this Professor Wu Yuanyang, and they modify this metric, and also it seems also approve this hydrospectral improved a little in some sense. Okay, so you say but it's so basically the problem is you have to realize the chiral symmetry breaking and also the linear rigid behavior, and also at the same time, you have to get the linear potential in a unified model, right? So this is the goal of our framework. And it seems actually, it turns out that, okay, it seems not that trivial, but still, but it's not complicated. So basically the system is, okay, so basically we have such kind of graviton-diniton system for a gluon system, right? This is a pure gluon system. This is, I mentioned just to get the, so this is diniton field takes this quadratic term, and then the diniton potential and this metric are solved self-consistently. So this is basically our background from the pure gluon system. So now we add light flavors. So actually this action is the same as the KKSS model. So basically this part is the same as the KKSS model. But we just, so the only difference is that this metric is solved. Actually, now of course this is a kind of coupled system. So basically, this is also coupled with these scanners. So basically, we have to solve this system again, because the total action is include this gluon system and also this flavor system. Okay, so this is a total action. That this is a flavor and this is a gluon part. So we have to solve this again self-consistently. And well, I don't want to get into the details, but the scenario is like that. So basically, we so basically at IR, so basically we put gluon condensation and also chiral condensation. So basically, we have the diniton field is due to this gluon condensation and this scanner condensation. This scanner field is due to this chiral condensation. And then after we solve this out, then we can get this chiral field. So this is the solution of the chiral field. This of course is our digital. This is the input. And then we can produce the hadron spectrum. I think this is quite good. I mean, this basically agree with lattice data. No, experimental data quite well. So basically, for lowest or ground states, so we have this Lamb-Goldstone pion mass. And also we have this chiral symmetry breaking between, so basically this splitting between the chiral partners. But for higher excitations, we can get this linear behavior. So this is due to this linear confinement. And in this framework, we also can produce the linear this counter potential for this within this solved by using this solved method. So basically, the linear confinement is indeed there. Okay. So basically, I think this work is in some sense I think it's a kind of a systematic framework that we can connect the QCD dynamics at IR to the geometry. And this framework actually works quite well. That basically, in a sense, we did nothing. Compared with the KKSS model, we just self-consistently solved out the whole system. So it seems we just so they solved how well. They kind of made some approximation, and we solved this system completely. And then it seems everything is correct. So the idea is, so I think so this framework resembles such kind of RG flow because it seems we put this IR dynamics here, and this digital field and this scalar field are dual with the gluon condensation and the chiral condensation. So it seems everything is clear. And I also briefly mentioned some results for QCD phase transition. Actually, this also works not bad. And we can compare with NACS data, and we can solve the equation of state and compare with NACS data. So this red dots from lattice data, and this line is solid line from our model calculations. But this is for pure gluon system. So you see, close to TC and also NTU-V regime, so this model works quite nice. But in this around 1.5 TC, our model is kind of a little bit different from this lattice result. And also the pressure density and the energy density. Also, I mean, it works at UV and also close to TC works good, but not good, not very good at around 1.5 TC. And also we can get trace anomaly. This measures this non-conformity around TC, and also this sound velocity square. So this is also quite, I would say, in very good agreement with the lattice data. And we can also calculate this screening, but though we don't know how to really extract the bi-screening mass. But we can calculate the heavy quark potential as a function of temperature, and then we can see that this linear potential eventually disappears, and then we can get some kind of screening. So this is this is similar to this, but not exactly the same. But for the Polyakov loop, this Polyakov loop, of course, indicates the color electric deconfinement. So this Polyakov loop, we can get almost exactly agreement with lattice result. And for the magnetic part, we need to calculate the special Wilson loop. And actually, we also get this magnetic confinement. And this is a special string tension. And also in quite agreement with lattice results. So I would say I am finishing because actually I'm also feeling tired. Yeah, I think, actually I have half an hour, then it's fine. Because for the outlook, I have something to say. Because I introduced some kind of, so basically, of course, and the challenge for us, as I said, that how you can get your QCD properties in the vacuum properties, or IR region QCD properties from your quarks and gluons at UV, right? So this is the most challenging problem for us. And of course,